Yeah.
So the goal of my presentation is to show that the set of continuous but nowhere differentiable functions on the interval 0 to 1 forms a second category. So before getting into that, let's just recall some definitions. So if we have a topological space X, a subset A of X is said to be nowhere dense if its closure has empty interior. And A is said to be of the first category or a meager set if it can be written as a countable union of nowhere dense subsets. If it can't be written as, if it is not of the first category, then we say that A is of the second category. So it can't be written as a countable union of nowhere dense subsets. And what the Baire category theorem implies is that a complete metric space cannot be written as a countable union of nowhere dense subsets. So for the problem at hand, our setting is that our space X is this space of continuous functions on this closed interval 0 to 1 under the soup norm. So that makes it into a complete metric space. So instead of looking at this set of nowhere differentiable functions, let's look at its complement. We'll call that D. So D is the set of functions f in X such that f is differentiable at some point X in 0, 1. So now what we'll show is that D is contained in a countable union of closed nowhere dense subsets of X. How will that help? So what we need to show is that X minus D cannot be written as such a union. If we show this, then we get what we want, because if we could have written X minus D as a countable union like this, by putting those sets together, we could have written X as a countable union of nowhere dense subsets, which we know is not possible. So just proving this will be enough for our purposes. So that's what we'll do. We'll show that D is contained in a countable union of closed nowhere dense subsets. So let's look at what happens when a function f is in this set D. In that case, we know that f is differentiable at some point x naught in 0, 1. So what that means is that this limit f of x minus f of x naught divided by x minus x naught, this exists as x approaches x naught. It converges to this finite, this number. So let's look at this quotient, this function. Since this converges to some finite number as we get closer to x naught, I know that there will be some open interval around x naught where this thing will be at distance, say 1 from this number. It doesn't matter what that distance is, just at some finite distance from this number f prime x naught. So I can find an interval like that. In particular, this quotient will be bounded on this interval. If I look at this function outside of this interval, I have a compact set. And this function is continuous on that compact set. So in particular, it's bounded on that compact set. So putting those two things together, what I get is that this quotient is bounded. So I can pick some small n such that the absolute value of this quotient is less than equal to n for all x not equal to x naught. And so I can rewrite this as I can multiply by mod x minus x naught on both sides. So I can rewrite this as mod fx minus fx naught less than equal to n times mod x minus x naught. And this will hold for all x in this interval. I've gotten rid of this x not equal to x naught condition. Okay. So if I define a set Dn to be all those functions in x such that there is some x naught for which this condition holds, then I know that the f I took here, it will be contained in the set Dn. And since for all functions in D, I can pick some n such that this entire thing is satisfied. What we get is that D must be in the union of all these Dn as I vary n from 1 to infinity. So not every function in this union has to be differentiable at some point in 0, 1, but every function that is differentiable at some point will be contained in this union. So I've written D as a union of these countable collection of sets. Now it will be enough to show that Dn is closed and that Dn is nowhere dense. And that's what we'll do. So first we'll show that Dn, each set Dn is closed. Right. So let's say we have some sequence of functions fk in Dn. And let's say that fk converges to some f. So this f will be in X. What we need to show is that f is in Dn. So we want to find some point x0 such that for all x, this condition will hold. So what do we know about the fk's? We know that they are in Dn. So I know that for each fk, we can find some xk such that this condition holds. So fk of x minus fk of xk, mod of that will be less than equal to n times mod x minus xk for all x in 0, 1. So let's look at this sequence of xk's. All of these are points in this interval 0, 1. So, and we know that 0, 1 is sequentially compact. So we know that we can find a convergent subsequence of this, let's say xnk. And those xnk will converge to some x0. What we'll show is that this x0 works for our f. So we'll show that mod fx minus fx0 is less than equal to n times mod x minus x0 for all x. So this is the quantity we have to put a bound on. What we'll do is we'll use the triangle inequality here. We'll introduce fnk because we have some control over that. So here, I've written this as a sum of 4 things. It's really just a simple application of triangle inequality. So here we've added in these terms fnk of x and fnk of x0. And so these two terms are looking at the difference of f and fnk at x and at x0. And we've also introduced this fnk of xnk term. Right. So, so the advantage of this is that for these two terms, I can use information about fnk. So I know that this difference, here I have fnk of xnk here. So I know that this difference has to be less than equal to n times mod x minus xnk. Same here, just with x0 replacing the x. So this will be less than equal to n times mod xnk minus x0. These two terms are looking at the difference between f and fnk at a particular point. So both of these will be, they have to be less than equal to this norm f minus fnk. So put together, it's less than equal to 2 times that norm. So I bounded this difference by this quantity. Here, everything is fixed except for nk. Nk is what we can vary. So what happens when we keep increasing nk? As we keep making nk bigger and bigger, fnk gets closer to f. So this quantity gets closer to 0. xnk converges to x0. So we know that as nk increases, this quantity gets closer to 0. And this quantity, this will be getting closer to x0. So this quantity will be getting close to x minus x0. So all that is to say that by choosing nk big enough, we can make this entire sum as close to n times x minus x mod x minus x0 as we want. Yeah. So yeah, and for each such nk, this inequality will always be valid. So taking the limit, what we get is that mod fx minus fx0 will be less than equal to n times x minus x naught, which is exactly what we wanted. So that tells us, and this, so here we hadn't assumed anything about x. X was just an arbitrary point in 0, 1. So this holds for all x in the interval. So f is in Dn. And so this shows that Dn is closed. Now what we have left to show is that Dn is nowhere dense. So it's enough to show that its complement is dense in X, because Dn is closed, so its closure is itself. So we have to show closure has non-empty has empty interior. So it's enough to show that complement has is dense. So for that, what we'll do is we'll approximate continuous functions by piecewise linear functions. How will that help? So, okay, let's say phi, let's call phi the set of all piecewise linear functions on 0, 1. So functions that consist of a finite number of segments like this. And let's say phi m is a subset of phi, where we are saying we are putting a condition on the slope of each segment. We want it to be steep enough. So we want the slope of each segment to be either greater than m or less than minus m. It has to, if it's a negative slope, it has to be less than m, minus m, and otherwise greater than m. So it has to be steep enough is all we are saying here. So now if you take any function in phi n, what happens is, okay, so take any function in phi n and take some point x naught, say x naught is here, look at f of x naught. If x naught lies on, say this segment, then no point on this segment will satisfy the, I should write, no point on this segment will satisfy this condition that functions in D1 satisfy. So basically no function in phi n can be in Dn. So phi n is contained in the complement of Dn. And what we'll do is we'll show that phi n is dense in X. So what we need to show is that given any function f in X and an epsilon ball around f, we want to show that there is an element of phi n in that epsilon ball. So right, so we want to approximate f by a function h in phi n. So what we'll do is we'll first approximate f by a function in phi, by some function g in phi. So we'll approximate f by a piecewise linear function such that g is, the distance between these two is less than epsilon by 2. And then we'll find some h in phi n, which is epsilon by 2 close to g. The reason for kind of having this intermediate g is, given, since f is an arbitrary continuous function, it's easier to approximate it by a piecewise linear function and not worry about the slope. And once we have a piecewise linear function, it's much simpler to look at. So after that, we start worrying about the slope of each segment. So if we find such an g and h, the distance between f and h will be less than epsilon. So, and that's what we want. So that will suffice. Okay, so let's first find our g. So this is what we have. We have this function f. The graph of this is what's drawn in black here. So we have this function f. The way we want to construct g is, we'll pick some points, so which are the blue dots here. We'll pick these points at which we want, we let g coincide with f. And between each of these segments, we'll extend g linearly. So that function by construction will be piecewise linear. What we have to ensure is that the distance between this linear segment and this graph of f everywhere is less than epsilon by 2. And for that, what we have to ensure is that the blue dots here, these are close enough. Okay, that's roughly what we're going to do. So let's just make that rigorous now. So we know that f is continuous on 0, 1, so it will be uniformly continuous. So I know that we can pick a delta, a positive delta, such that as soon as 2 points are at distance less than delta, distance of f at those points will be less than epsilon by 2. We can pick a delta like this. And once we have this delta, we can pick a natural number capital N such that 1 by n is less than delta. So what we'll do is we'll pick these blue dots to be, they'll be equally spaced. In this diagram, they're not equally spaced, but in the construction, we'll space them equally. So these blue dots will be all points of this form, k by n. So all these points are a distance 1 by n from each other. And once we have them, we'll do what I'd said earlier. So we'll define G. G will be equal to f at these k by n. And between two consecutive k by n's, we'll just extend G linearly. So yeah, so what we have to ensure is that for any x, G of x and f of x are at distance at most epsilon by 2 from each other. Okay, so for x equal to k by n, we don't have to check this because G is equal to f, so distance is 0. For any other x, so x has to lie in some interval of this form. So say if x were here, this would be the interval we would be looking at. It has to lie between two consecutive points like this. Now, right, so x is a linear, G of x is a linear combination of f of k by n and f of k plus 1 by n. And in particular, we know that there is some t between 0 and 1, positive t, such that G of x is equal to t times f of k by n plus 1 by t times 1 minus t times f of k plus 1 by n. This is what we know about G of x. Right. And we'll just write f of x this way as t fx plus 1 minus t fx. The reason for that is, so we want to look at this difference, mod gx minus fx. We want to bound it. So we'll use a triangle inequality. So it's just because of that, just to introduce these terms involving t and 1 minus t. So yeah, so I have these expressions. So we'll plug those in here in mod gx minus fx and use a triangle inequality. So we'll club the terms involving t together, and we'll club the terms involving 1 minus t together. So this thing becomes less than equal to t times mod f k by n minus mod minus fx plus 1 minus t times mod f of k plus 1 by n minus f of x. Now, whatever is in these two terms, since x is in this interval, x and k by n are definitely at a distance less than delta from each other, and same for these two. So by the choice of delta, we get that this thing should be less than epsilon by 2, and same for this thing. So this full put together, this becomes mod gx minus fx less than equal to t epsilon by 2 plus 1 minus t times epsilon by 2, which is equal to epsilon by 2, which is what we wanted. Right. So we found our g. Now, given g, we want to find h that is distance at most epsilon by 2 from it. So in general, what we'll show is that given any piecewise linear function, we'll show that there is a function in phi n which is at distance at most epsilon by 2 from it. So just to illustrate what we'll do here, this diagram. Okay, so here, just for ease of explanation, I've taken a very simple case, just where the function has just these two segments drawn in black. Right. So we want to, right. So we have this function. The epsilon by 2 ball around it looks something like this. So we have this band around it, where the distance between these two things is epsilon by 2. We want a continuous function which will fit in within this band. And we want that function to be from phi n. Now, similar to how we had found g, we'll construct h in the exact same way, very similar way. So on each segment, we'll kind of pick these blue, these points, at which, so at every other point, we'll let h coincide with g. And at the other points, we'll let it be just g plus epsilon by 2. So the slopes of all these will be, whatever these slopes are. What we want to ensure is that this slope is at least, the modulus of that is at least n. So again, all we need to ensure really is that the blue dots are close enough to each other. So right, so let's yeah, so here let's see how to do that. So again, just for so that the expressions we have to write down are less messy, what I've done is I've just illustrated the case for one particular segment. I've just taken this segment, and I've we can shift it and rescale it so that this point coincides with this 0, and so that the function we get is on the interval 0 to 1. Just shifting and rescaling this segment is all I've done, just so that the expressions we have to write for g and h are simple. Okay, so right, so here here the slope, we are just calling it L. And so again, we've taken a very simple case. The function g is 0 at the point 0. So we have a very simple expression for g, which is g of x will be L times x for any x in 0, 1. Okay. So right, so I want to pick some 2n so that these blue dots will be spaced 2n a distance 2n from each other. Right, and why the 2n? And that's because we want to kind of split the case between odd and even points, because these are sort of alternating between being on this line and being on this red line. So what I want to do is that at these points, 2k by 2n, I want to define h at those points to be the same as g. And at the odd points, at these points, I want to define h to be g plus epsilon by 2. And again, so we have a simple expression for g of a point. So I've just plugged that in here to get this. This is what we want. Now, now the condition on 2n is that the slope of each of these has to be at least n. So here I've just split that in two cases. This case is looking at this sort of, the positive slope lines of positive slope, and this case is looking at those of negative slope. So I want, yeah. So yeah, once I have this, I want mod of this to be greater than n. Here, we can just plug in these values that we have, and in this case, it comes down to L by 2n plus epsilon by 2. So the epsilon by 2 is coming from this term, and L by 2n survives because the difference between these two will be L by 2n. And put together, that becomes 2n times this quantity. Similarly, in this case, exact same thing. We just plug in these values and we get 2n times this quantity, L by 2n minus epsilon by 2. We want both of these things to be greater than n. To ensure that it's just enough to take n big enough such that 2n times epsilon by 2, which is n times epsilon, just that should be greater than n. And that will be enough. So once we pick that to be our n, everything will work out. I can define h this way, and the slope will be greater than n everywhere. So h will be in phi n. And so we are done. And so that finishes the proof. Yeah. So that's all I have. Yeah. Thanks.
Yeah, questions? Anything? Do you want to go through something again?
Can you take, Urshita, can you take back to the starting of the proposition again?
Yeah.
I mean, this one, the one we proved just.
Sorry, which proposition?
The one you were trying to prove now.
Yeah. Firstly. Yeah. So the goal is to prove nowhere differentiable functions cannot be written as a countable union of nowhere dense sets. And the space we are looking at is continuous functions on 0, 1. So we reduce that to showing that the complement of this, which is set of functions which are differentiable at some point, we reduce this to showing that D is contained in a countable union of closed nowhere dense sets.
Ah, okay, yeah, yeah, yeah.
Yeah, fine. Is that fine?
Yeah, yeah, it is fine. Mm, thanks.
Yeah.
Okay. So, any other questions from anybody else? Okay, it was good. So, if there is no question, we will end the session. Okay, we will meet tomorrow. Bye.